Okay.
Okay. So our next speaker is Shlomi Kotler, and he will tell us something about the entanglement of macroscopic objects. So please.
First, I'd like to thank the organizers for the opportunity to talk. So this is work that I did at NIST in Boulder. And I will talk, what I'll talk about today is entanglement of two macroscopic objects. Let's start by describing the objects. So the objects are drums. I'm going to refer to them as drums. This is the left drum and the right drum. In what sense are they mechanical objects? You can think about it like trampolines. They go up and down and up and down. So that's their mechanical motion. And it's like a drum, literally. And when I say macroscopic, what do I mean? So the scale size of each one of these objects is between 10 and 20 microns, which is the thickness of the human hair, for those of us who still have hairs. So you can feel it and say, okay, the diameter of this is something I can feel. So that's macroscopic. And entanglement is nothing more than correlation. So take one of these drums. You can characterize it by its position and momentum, right? If I know the extent of x and p, then I know everything about it. And I have two of these objects. So correlation means that the position of this drum is correlated with the position of that drum. And the momentum is correlated with the momentum. But you could say, well, that's just correlation. What makes it quantum? Well, usually what makes things quantum is that you break a certain bound. There's a certain bound beyond which classical physics doesn't allow you to correlate. If you go beyond that bound, then you can claim that that's entangled. And that's what you see on the upper left graph. You see that there's this 1/2 line above which everything is considered classical and below which the system is quantum mechanically correlated or entangled. So that's it. That is not the outline of the talk. That is the talk. So if you want to leave, this is a good opportunity for you. Everything else is details. Now I want to segue into the details of this by going back to the early days of quantum mechanics and thinking about atoms. Quantum mechanics was never envisioned originally in the context of big objects. It was envisioned for small objects, electrons and atoms. More specifically, it was a mechanical theory because it was considering the mechanical motion of the electron, celestial motion around a nucleus. And by quantizing this motion of an electron, people were able to explain light that's coming out of elements. And specifically, they were able to explain spectroscopy. Okay?
This is the old quantum mechanics.
This is the good old quantum mechanics.
That's the official term is old quantum theory. Or
so I'm going to claim that the new theory is a subset of the old theory. Let's see by the end of this talk if you agree.
I disagree.
Well, that's the end of the talk. Let's disagree in 30 minutes. Well, actually 27. Okay, so spectroscopy 101. I know some of you are experimentalists, some of you are theorists. What do I mean by spectroscopy? The goal of spectroscopy is to know the atomic transition. And that's what we care about, to know the energy gap between two levels of an atom. How would you do that? You will take a source of atoms and then just spray it. Those atoms have some sort of an atomic frequency. And how do you know an atomic frequency? You put some sort of an oscillator and you scan the frequency of the oscillator. When you hit a resonance, then you know that you have found your atomic transition. And how well do you want to know it? To the best of your ability. You want to know it as accurate as possible. What will be the first limiting factor? The transition time of the atoms through the interaction with the oscillator. If they go really fast, you have very poor resolution. If they go slow, then it's better. At the beginning of spectroscopy, people were trying to make bigger sources, so they have a longer interaction region, and so a better resolution. And then came the famous Ramsey technique. Without going into the detail, the whole idea of Ramsey is that you can split it to 2 oscillators, and then it's the time between oscillators that gives you the resolution. Just to give you a sense of scale, here's Ramsey right after his bar mitzvah. And you can see that huge machine that is basically trying to accommodate for this beam of atoms, okay? What is in our way here is the fact that the atoms are moving. If they were just kept without moving, if they were still, then I could probe them. So enter Wolfgang Paul and Hans Damel that says, let's trap them. Let's keep them in one point. And now I have the age of the universe to probe them and have a very good resolution. And now what gets in my way? Even if you trap something, it can have thermal motion. It can jiggle and wiggle around, and then the Doppler shifts will limit your resolution. Enter Dave Wineland that says, well, let's cool them. Let's trap them so they don't move, and let's cool them. And when they're very cold, no Doppler shifts, I can really know the atomic transition. By the way, all of these people won the Nobel Prize essentially for their contribution to spectroscopy. So let's look at the impact of trapping and cooling on spectroscopy. Here's my atom, and it has an atomic transition, roughly 10 to the 15 hertz. What happens when it's at room temperature, 300 Kelvin? It will have a Doppler shift of about 1 gigahertz. So because of this motion, this annoying motion, I will have an atomic resolution of about 1 part in a million. Okay? And here's how it looks like. It's like a very broad peak centered around 10 to the 15 hertz. What happens if I trap this atom and cool it? Well, now it has, I don't know, say a motion of 10 megahertz. Then what's going to happen is this is how the spectrum will look like. I will have very fine combs, and now I can really know the atomic transition. Let's look at data. So here's data taken from a single atom, and you can see that center peak. That's a very fine comb, and you can even see motional sidebands going to the sides. And if you zoom in on the center and really take a careful measurement done by my colleague Nitzan, then you can get a resolution that's now 60 hertz over 10 to the 15 hertz, or 1 part in 13. What do you think the record in knowing an atomic transition? What? About a few parts in 10 to the minus 19. It is the best physical quantity that we know how to measure today. Okay? So summarizing all of this, from the perspective of people who are doing spectroscopy, motion is a nuisance. I want to know about the internal degree of freedom. Stop the motion, trap, and cool. Now, at the same time, those people were doing their advances in the late 1980s and 90s. On a separate corner of the planet, in a separate field, these people were thinking about quantum information. They thought about a new model to do computation called qubits. And at the time, there was absolutely no connection between the two communities. And why would there be, right? Until these guys appeared on the scene, Serac and Zoller, I'm telling you a story you know, and they understood that these two communities are actually can solve the same problem together. And what they realized is that motion is not a bug. It is actually a feature. You can actually use it. And in 1995, they wrote this paper. Look at the title, Quantum Computation with Cold Trapped Ions. Now that was the key. Cold trapped ions. That was the theory paper. Same year, the Wineland group was able to implement the first entangling gate. You already know this gate, but I'm going to repeat it so you see the beauty of how spectroscopy gave quantum information. And by the way, this 1995 is the beginning of quantum information experimentally, at least the gate model. Okay, so just a reminder of how you entangle ions. So here's the energy energy gap of a single ion, ground and excited. Take this ion, put it in a trap, and now you have to account for the motional degree of freedom, and you will turn on a laser. What kind of lasers are available? Well, just ground and excited, just a sigma X, which is boring. You can have a blue sideband, which is ground to excited, and 1 quanta of motion, or a red sideband, which is ground to excited, taking away 1 quanta of motion. What does the blue sideband does? It's an entangling operation. It entangles the internal degree of freedom with motion. It takes you from ground and no motion to ground motion plus excited and 1 quanta of motion. What does a red sideband do? It's a swap gate. It takes a superposition of internal degree of freedom and turns it into a superposition of motion, of external degree of freedom. And that's all I need. You want to entangle 2 ions, put them in the same trap so they have a common mode of motion. They're moving together. Start with both of them in the ground state, no motion. Now I'm going to apply a blue sideband on the left ion. I will entangle that ion with the motion degree of freedom. But that motion degree of freedom is common mode to both of them. Now I'm going to do a red sideband on the other ion and swap the superposition of motion into the internal degree of freedom. And now I can tensor out the motional degree of freedom, and I've created an entanglement. So what's beautiful about it is that an electronic degree of freedom and another electronic degree of freedom, 2 atoms, are talking through a harmonic mode, one by entangling with it and the other by swapping with it. And we'll come back to this later. Now, in the past, I want to say maybe 11, 12, 13 years, we no longer consider quantum mechanics, physical quantum mechanics, to be limited to just ions, as you see on the left. We are also considering to take very massive objects and put them in quantum states. And in fact, it goes all the way from ions to test masses of LIGO. There's a logarithmic scale of different systems that we consider to be quantum mechanical, and that we do it in the lab, that we employ quantum mechanical manipulations in the lab. And now I can introduce the hero of this talk, which is this drum, okay? So it's a mechanical object, thickness of a hair. Its mechanical frequency is around 10 megahertz. It's governed by its diameter, about 20 microns. And it's basically aluminum, very clean aluminum on sapphire. When it moves, there are about a trillion number of aluminum atoms, so very far from a single ion, right? A trillion atoms going up and down in this collective motion. But the most fantastic number about this drum is that it's 0-point motion. It's a harmonic oscillator, so it's valid to ask, what is the 0-point motion of this object? And the answer is it's a femtometer. It's on the order of the diameter of a proton. If you want to see quantum phenomena of this object, you have to be able to resolve quantum fluctuations that are smaller than the diameter of a proton, okay? So that's what makes it maybe a little bit challenging. Okay, how do I talk to these drums? It's a mechanical object, great. How do you talk to it and interface it? And the answer is, you use electromechanics, which is a fancy way of saying if an object moves, the electromagnetic field knows. Anyone that's ever got a speeding ticket knows about it, right? So how does the police radar know that you've been speeding? They literally shoot microwave pulses at the moving vehicle and look at the reflected microwave. The reflected microwave has Doppler shifts. Looking at the Doppler shifts, they know your velocity. Okay? This is essentially what we do with the drums. So here's my top plate. This is a side cut of my top plate, and I want to know where it is. Well, how can I do it? I'll just put a bottom plate, and now I have a capacitor. But it's not just a capacitor. It's a capacitor whose capacitance depends on X. Okay? So if X moves, C changes. How do you measure capacitance? Nobody measures capacitance. We usually add an inductor, and now we have an LC circuit. But it is an LC circuit whose frequency depends on the position of the top plate. Basically the same Doppler idea. And now if I couple this to the outside world and look at the spectroscopy, I get to see a boring LC circuit peak. But now if I add a pump, I will see, surprisingly, 2 sidebands. A red sideband and a blue sideband. And let's try and understand them using conservation of energy. So this sideband is a beam splitter interaction. Why? Because I came with a microwave tone, and then I got a reflected microwave tone at a higher frequency. Where did it get its energy? By sucking a phonon from the mechanical objects. I traded a phonon with a photon. Okay? This is a two-mode squeezing operation. I started with a photon, a microwave photon, and now I got a scattered microwave photon that has less energy. Where did the energy go? It went into the mechanical objects. I'm generating phonon-photon pairs that are actually two-mode squeezing or entangling them. I can get to choose which one is dominant by, and it's called a blue sideband and a red sideband, exactly like the trapped ions. And I can get to choose which one of them is dominant by moving my pump one way or the other way. So it's a programmable, if you wish, beam splitter and a two-mode squeezer. Okay, that's all I need. All right. And now, when you look at these drums, now you understand why they have this squiggly. This squiggly is nothing more than an inductor, turning it into an LC circuit. So if you look at one of our devices, it looks like a regular microwave box, and there are copper traces all the way to this transparent sapphire chip. If you zoom in on the chip, you get to see four different experiments. And now if I zoom in on one of them, you get to see the device. But here there are two drums. Why two? You cannot entangle one. You got to entangle at least two entities. So that's why I have two. How will I talk to them? Oh, we're warming up, How will I entangle them? Well, I'll basically couple them to the outside world like this, or if you wish schematically, it's just going to be two capacitors. Each one of them is changing the LC circuit. They have two mechanical frequencies, and the entanglement protocol you already know by now. I'm going to take my LC circuit, and I'm going to put a red sideband with respect to one drum and a blue sideband with respect to the other drum. The red sideband swaps energy between an LC circuit and a mechanical object. The blue sideband entangles an LC circuit with the other mechanical objects. If I make sure these two scattered sidebands overlap so that I cannot distinguish between them, then I will generate phonon-phonon correlations. And if I do it very well, maybe I'll get entanglement, maybe not. That's the scheme. Does it remind you of anything? It should remind you of the scheme, the Sirach-Zoller scheme. There, it was two electronic degrees of freedom talking through a harmonic oscillator, which is motion. And here are two mechanical oscillators talking through a shared electronic degree of freedom, which is an LC circuit. Okay? It's just the same scheme, only reversing the roles. All right. Let's look at data so that we get used to how does a measurement look like in the system. And I'm going to start with data of a single drum. Okay? So when you measure a single drum, you get a point in phase space, which is what was the position and what was the momentum of the drum when I was measuring it. Okay? Usually you don't do experiment once, you repeat it many times, and these are going to be histograms of position and momentum. And when you repeat it, you get scatter, and if you repeat it many times, you get to see this. What is this? What does this state describe? Do you have a guess? What?
Coherence.
Coherent state? I wish. No. It's a thermal state. What you're looking at right now is nothing more than temperature. The drum wiggles, and it's very hot, and I get to see a very big two-dimensional Gaussian. But I can cool it. I can apply various techniques so that it's colder and colder and colder. And if I apply a cooling technique, this is what I will see. And you can ask me, okay, it's a colder drum. How cold is it? And the answer is it's pretty close to the ground state. It means that if you looked at the drum like so and asked me what's the variance of X, and I would say roughly the diameter of a proton. Okay? And that means that we can resolve those fluctuations. All right. just for fun, let's look at a movie where what we did here, we took the drum, we cooled it, and then we let it thermalize with the environment, okay? And if you do that, here's how the movie looks like. Basically, as it reaches thermal equilibrium, the Gaussian warms up. So basically, you're seeing temperature.
What would be the size of the 0-point motion if you're at 0 temperature?
At 0 temperature is roughly what you just saw. Yeah. So what you saw at the beginning is 0.4 quanta, roughly. So it's not 0, it's 0.4. But between friends, it's okay.
The environment is the circuitry, or
The environment, the environment is, I'll show it, but it's the dilution refrigerator. Okay. All right, so now we got to talk about entanglement as fast as humanly possible.
You didn't tell what is the frequency.
Of what? 10 megahertz. Okay. So how would entanglement look like? If you apply an entanglement protocol, the kind we just described, at the beginning you'll see nothing interesting. You're going to see that the position and momentum distribution of one drum becomes hot. The position and momentum of the other drum look like they're hot. Nothing too interesting. If you look at cross correlations, all of a sudden something gets revealed. Here's the position versus position. So the position of one drum versus the position of the other drum, and momentum of one drum versus the momentum of the other drum. If I let the theory roll, here's what you'll see. You'll see, yes, this one looks hot, energetic, and the other one looks hot, meaning energetic, but there's a very clear correlation and a very clear anti-correlation that you can see between the two drums. Position, position, and momentum, momentum. Does that prove entanglement? No. It just shows you that they're correlated. Now, everyone that's ever driven a car knows that the wheels of the car are correlated. Otherwise, you will, it's not, we talk about correlations and we say that they're mechanical. No, we kind of rely on having correlations even in the classical world. So to know that something is entangled, you have to show that the correlations are strong enough. In the year 2000, Simon and Duan found the criteria for this system that's very nice. They said, well, do this. Take your system and measure position momentum of one drum, measure the position and momentum of the other drum, and now you get 4 random variables. Repeat this measurement multiple times, and then what can you do with 4 random variables? You can form the covariance matrix. And they said, if you give us the covariance matrix, up to calculating polynomials and maybe a square root, we can get you a single number that will answer the question. And that number, if it's bigger than a half, for sure what you're looking at is classical correlations. And if it's below a half, it's entangled. Now, a lot of times when I show this slide, people get annoyed and they say, why aren't you showing us the formula of this nu minus? Because to me, square roots of elements doesn't tell me anything. Let me explain not the formula of nu. Let me explain this 1/2. What does it mean? Where is this 1/2 coming from? So you have this drum, and it's really a randomly moving drum. And you have this drum, and it's really a randomly moving drum. But when you measure them, you somehow see that they keep appearing really close to each other. If they appear to be very close to each other at a point where it's closer than their own 0-point motion, then they've broken the bound. Same for the momentum. If the momentum of one drum agrees with the minus of the momentum of the other drum to an extent that is way better than their own 0-point motion, then you have an entangled state. It's breaking the 0-point motion of each one of them that makes this bound meaningful. Okay, so the price of listening to what Simon says is you have to develop an experiment where you can measure position, and momentum with a very good resolution. And this reminded me of a book that you can buy on Amazon that says that a PhD is not enough, a guide to survival in science, and a PI is supposed to give it to their graduate PhD students so that they don't get don't get excited. There's much work to be done. So what Simon and Duan is telling after they finish, no. You want to, just when they're so happy that they finished their PhD, you want to hammer them down with that, And so to me, what Simon and Duan were teaching me that the entanglement is not enough. you have to be able to somehow observe this entanglement. It's going to be a hard task. In fact, the most hard in this experiment. And so when we asked for an artist to depict this difficulty, this is what we came up with. You have entangled drums, fine. But as an experimentalist, 5 minutes. I'll never get, okay. Let's finish with this slide. Okay, so you want this to observe this entangled state, but as an experimentalist, essentially, all you have to access is the shadows behind it. And so looking at the shadows, there's no entanglement. How do you devise an experiment where you can actually shed light on the entanglement and not on the shadows was the main experimental difficulty. And looking at time, I don't have time to discuss it, which is good because it's really complicated and technical. Okay, all right. And so let me skip to the data. Let me skip. Okay. And if there's time later, I'll talk about the experimental difficulties. Okay, let's look at data of entanglement, and we're talking about not the shadows of it, but actually looking at the drums. So let's start with the energy of each drum, okay? So the y-axis is how much energy is in each one of those drums, and the x-axis is how long am I employing this entanglement protocol. And this is what the theory would say if I did a red sideband and a blue sideband that are separate from each other. The blue sideband will just heat up one of those drums, and the red sideband will cool the other drum. But I'm not going to do that. I'm going to make sure that the sidebands overlap. And when they do, I see something interesting. This drum starts to lose energy and then gain energy. This drum starts to gain energy exponentially and then breaks off polynomially, and they're doing it somehow in correlation with each other. If you plot the theory of entanglement, it fits. It's not a proof of entanglement. Next, let's look at the data of the correlation. So position of one drum, momentum of one drum, position of the other drum, momentum of the other drum. As you entangle more and more, energy is being pumped into the system. Now let's look at the correlations because they're supposed to tell you what's going on. Again, this is position of one drum versus position of the other drum and momentum versus momentum. And let's look at the data. Okay, clearly there's a correlation between the position of one drum and the position of the other drum, and an opposite correlation with the momentum. But does that make it entangled? No. You have to make sure that you satisfy Simon and Doohan. All right. So let's look at the covariance matrix. So at the beginning, before I had any time to entangle, I get a diagonal covariance matrix. It's pretty boring. And when I'm entangled, you get to see a very positive and negative off-diagonal elements. If you wish, this covariance matrix is the scientific version of the shadows no more, right? You're looking at entanglement in the data. Okay, and now here's the bar to beat. So 1/2, anything below 1/2, it's entangled. Anything above 1/2 is a classical correlation. This is what the theory would predict, and this is the data. So it looks like it works. We've entangled.
What's the x-axis?
How long, the duration of the entanglement pulse. How long am I giving that system chance to entangle? Okay? And now, when we got this data, we were working with a theory group led by Emanuele and Scott Glancy, Izad Shojai, Alex, and Sean. And they said, well, just wait a minute about this entanglement business of yours. And they said, we have a dogma of how you should approach an outstanding result, and you have to be very careful. Number one, you have to start working with us as soon as possible, before you even have data. So work with us. And they said, okay, fine, I'll work with you, a nice bunch of people. And then they said, well, now that you're taking data, let's train not in terms of neural networks, just to see that we have no bugs, that we didn't do any mistake, that we didn't multiply by 4. Let's make sure that the analysis makes sense, and let's make sure that the analysis and the data match. And then And then, and this is the part where they didn't tell me at the beginning, and I wish they had, you throw the data. You cannot use any of the data that you used when you were developing your protocol. And now comes the last part, which is guigate gu, which means you get what you get and you don't get upset. It's 9 p.m. You press a button and you take one fresh copy of the data. That's it. Come back in the morning, look at the analysis. Can't do anything because it's already been fixed. And either it's entangled or it's not entangled. If it's entangled, good, we publish. If no, you're fired. But you cannot change the analysis anymore, okay? And I wish they had told me about that. So, throw away the data. We had one fresh copy. Press a button, go to sleep, and see if you have a job in the morning. So this is the result. And so as you can see, and standing here I still have a job. So basically you can see that, that we crossed the bound with good statistical significance, and we can, we were NIST, so we actually put some error bars on it.
Well, what happened to the short times?
At short times you're fighting the residual thermal energy. So remember I told you that you don't start at the perfect ground state for each one of those drums, but it's like 0.4, 0.2, 0.4 quanta. You squeeze first that, and then you go below the entanglement.
So in the beginning of zero, I guess you have no entanglement.
Yes.
How long does it actually take to reach, to get entangled?
Well, right here, as you can see, when I cross here, I don't know, 3.5 microseconds, which is just a manifestation of how much I'm pumping. I pumped the hell out of it, and it,
It goes into a steady state.
it goes into a steady state until decoherence kicks in and then destroys it. So you have about, decoherence starts to kick in at around 200 microseconds. So we stopped an order of magnitude before decoherence could ruin the state.
Does this include like measurement errors, or is this?
Everything, includes everything, yes. So this is,
Usable entanglement?
it's usable entanglement, thank you. Yes, it's usable entanglement. You can, use it at home. All right, this was done at the fabulous group at NIST with my back then supervisor, John Tufel, and people I highlighted, Gabe and Brad, the mechanics team, and the lovely theory group that nearly destroyed my career. All right, and so what's next? Well, I looked at all of these talks, and I really envy all of you guys. But thinking about the history, we started in 1995 with entangling 2 ions. That's all we had in the field. And now it's 2022, and this is what you have. You can do complex computation and algorithm and Quawa and whatever you guys said for the entire conference. Basically complexity that's leveraging this two-ion entangling gate in 1995. And so hopefully people like myself and my colleagues will add another arrow, which is the arrow of mechanics. Now we have entanglement of mechanics. We'll slowly start. So, maybe in 10 years from now, it will be QAOA with mechanics and neural networks and everything you guys just said, hopefully based on entangling just 2. And so I'll end with a famous, my favorite book, an undergraduate book of Feynman. And in his volume 3, which was dedicated, I'm not kidding you, this is open volume 3. It's dedicated to quantum mechanics. One of the front pages is Feynman banging on drums, literally drums, 2 drums. And so hopefully I was able to convince you that we can also play the quantum drum. And with that, I'll take your questions. You have a minute.